Hey Munchkins, it's time for some math help. Yes, yes it is. Alrighty, so this is lesson 3, which is a prime number. It's a Fibonacci number 2 as well. I mean, what I said last time about specific words being used in math. Okay, I mean TOO. Okay, lesson 3. We're going to build on a little bit on the last lesson, which was about expressions, but today we're just going to deal with numbers. Well, no, that's not true. That's not true. We're going to do with numbers, and then we'll extend that over to the letters, to the variables. Okay, and that the same rule applies to both knowing what the number is, knowing what the value is, and not knowing what the value is. The rules will still apply for the rule for exponents. Okay. So, pencil, get it out. We do math with pencil, maths, whatever. Calculator might be helpful today. I'll show you some things that this can help you with, but of course I want you to use your brain. Homework paper. Yes, this cool algebra reference sheet. If you didn't get one in class, you can download one at that website there, eeweb.com, a cool electrical engineering website, and this is very useful. Some of our rules for today are going to be right here. So that's just for reference. You can make a note of that in your notes, which, well, there's my notebook. And just, if you're a really curious person, bring along your collection of dead, whatchamacallums here. Do you see the little pterostigma on those wings? Let's get on my face. See the little markings there? They're like these little weighted doodahs. You should watch the Smart Everyday video on that. It's super duper cool. These guys are like the fighter pilots of the insect world. There's another dead one out there. I'll get it later though when you guys aren't looking. And okay. Righty then. So, here we go. You ready? Too bad. New concept is about exponents. Maybe it's not a new concept. Exponents is a way of doing things in a shorthand kind of format where you're going to have a base that could be a letter or a number, like yesterday or the last time, and then to another number, or it could even be to a letter, but today we'll do it to a particular number. It's a way of writing a bigger number in a more condensed form. For instance, 8 could be written like that, but we could also write it as 2 cubed, which just means 2 times 2 times 2. All we're doing here is counting up how many times we're multiplying the same number by itself. And I'm going to put little onesies up here so that you can see the little rule. 2 to the power of 1. That first 2 is just there once. The second 2 is there once. The third 2 is there once. So we say, I got 1 plus 1 plus 1. I got 3 of those, so I can write it as base 2 power 3. Base 2 power 3. Now there are all kinds of bases that are used in math. We usually use base 10 in particular because we have 10 fingers, so we use place value. There are other base systems like binary, which is a base 2 system. So we could think of it like that, or you just think of it as a number, a big number that can be expressed as smaller pieces, usually prime factors, multiples of prime factors. Okay, so we're going to use that idea here that 2 cubed is 2 times 2 times 2. I'll tell you what it is not 2 times 3, so don't do that, though that is a common algebra mistake. Don't do that. Realize that anytime you got something to a power, it's telling you how many times that base is being multiplied by itself. Alrighty then. So this is the base, the numbers, and the other 2 was the base and 3 was the power. Okay, so we can do it just with numbers. That's pretty boring. Your calculator can do that, but you should learn to use your brain. So if you had something like 7 cubed, that means 7 times 7 times 7. So you can even start doing that. You like 7 times 7 is 49 times another 7. You could do that by hand pretty fast, pretty sure. 49 times 7, I got 280 and 63. I'm doing this from left to right, which you will at some point learn how to do. So we're going to have 343, I think, for our answer for 7 cubed. You can always double check that on a calculator. There's a very useful little button here. You go 7, and then if you want to say to the power of, it's right over here. It's called a caret. You see that little arrow that goes up? And it'll raise your little cursor up, and you can type in your exponent and then hit enter, and you can't probably really see that very well. There it is, 343. So the calculator can be a nice way to check those things, but they're small numbers, okay? Just, you're gonna have to do that stuff at some point. Cut the cord, people. Same thing can be true of decimals. We could take 0.3 to the 4th power, which means 0.3 times 0.3 times 0.3 times 0.3, 1, 2, 3, 4 times by itself, and we'll get a very, very small number. But what we want to do is we just want to realize what that means, okay? We're not multiplying the base by the power, we're multiplying the base, the power number of times. Okay, so if it's just a number, a whole number, it could be a decimal, it could be a fraction. I'll show you a couple of these because this is important. I'll kind of introduce another rule. If we did, and I'll just do cubed again. This means 1/2 times 1/2 times 1/2. It doesn't mean 1/2 times 3. It means 1/2 multiplied by itself 3 times. And if you remember the rule for multiplication with fractions, you multiply the numerators across and you multiply the denominators across separately. So this actually is 1 times 1 times 1 over 2 times 2 times 2. So 1 times 1 times 1 is 1, and 2 times 2 times 2 is 8, which we did previously. So you'll get 1/8. But let me show you another way that you can think about this. This is also a rule that applies to taking powers of fractions. And that is, we could rewrite this as 1 cubed over 2 cubed. You can separate it in 2 little mini problems and do the math there. You're like 1 cubed is 1 and 3 cubed is 8. And there you go. There's your answer. You get to it a little bit faster. Right. So that's kind of a little rule that you can follow for fractions. Here's another one over here. So if I want to use my little fast rule, I'm going to just take each part of the fraction to a power. So 2 squared is 4 and 3 squared is 9. There's your answer. You don't have to go 2/3 times 2/3 and try to think what in the world that is. There you go. It's 2 squared over 3 squared, which is 4/9. Okay, another special one is when things have a base of 10. That's our normal number system is base 10. So the cool thing about base 10, taking things to powers here, is that basically that power tells you how many zeros to write down. That's a little shortcut. I mean a pattern. Pattern means shortcut in math speak. So I can put that 1 down, and then I can just say, well, it's asking for 3 zeros, right? And there's my answer. Because if this was 10 to the 1, that's just 10. And if it's 10 to the 2, that means 100, which has 2 zeros. So I know that any number here is the number of zeros that I'm going to have there. And it works with base 10, okay, because that's our number system. Every time we move over 1 decimal place, we've multiplied or divided by 10, so that's a little quick way of doing that. And base 10 is awfully handy because later on we're going to talk about scientific notation, and we're going to talk about powers of 10. You talk about the scale of the universe. I'm going to leave a link in the description below or in the comment section. You can go to see that little demonstration of zooming way in and zooming way out and the size of things. We'll talk about that in about 2 minutes and 28 seconds. Okay, now let's put things together. We can also have x. We can have a variable to a certain power, and that means x times x times x in the same way that 2 cubed meant 2 times 2 times 2. So we can pull it out and we can put it back together. Each of these x's is there once, and so basically what we do by using the product rule is we are turning multiplication into addition. We're turning multiplication into an addition problem. You see, if all these have the same base, all we have to do is add the exponents. There used to be a thing called a slide rule. I have a paper one somewhere, and it basically does that. You slide these things over, and then you go and you count things rather than multiply things to get an estimate for your answer. Very handy little tool. It follows what's known as a simplification of this process. It's called the product rule. And I'm using it and just explaining where x cubed comes from. I could write this as x to the 1 times x squared, because x squared is x times x. Okay, so I could just put two of those together and then have the third one and realize that basically what I'm looking at is a little addition problem up here in the exponent. 1 plus 2 is 3. So I can split it up really any way that I want to, because I'm keeping everything true to its meaning here. Product rule says if we got these two exponents, m and n, and that if they are real numbers, okay, remember lesson 1, we broke that down to what that meant. And as long as the base here, x, is not equal to 0, because that would be pointless, this rule applies. If these bases are the same, all we got to do with those powers is add them together. Okay? All we got to do is add them together. So you should have that written down. Pause me right now and write that down. And then we're going to keep going. Right. Let's take that rule here. And I'll use a different letter than X. I'll use the letter A. And we'll just pick some ridiculously large. There. Here we go. You don't want to go A, 7 A's and 5 A's and then like count up all the A's, though you could do that. This rule says all we have to do is that since both of them are A's, I can do a little problem up here in the exponent and I get my answer. So this equals A to the 7 plus 5 is 12. I could split this one out. I got A times A times A. 4, 5, 6, 7, and this one here would be another A times A times A times A times A. I'm going 7 of these, and I got 5 of these. Is 12 of these. Make it as straightforward and simple as possible. There. You could have x squared and x to the 2 again, and then we're just going to go 2 plus 2 is 4, and we could even do a bunch of combination of things. And all we got to do is, these ones are like each other, the base is the same, that's the most important thing, and there's kind of an understood 1 right there. So this one equals x to the 2 plus 1, and that white cube would sit there all by itself. I don't know if I needed to do that, but there you go. That's kind of a good application of it. We're going to find things that are like each other and we're going to smoosh them together. There is an example in the book, example 3, about powers of 10. And let me cover that really quickly because this is what's called scientific notation. Earthquakes are measured in a base 10 system. And so here we're looking at the magnitude. How much bigger is the answer than this first number here? We've got 10 to the 9th compared to 10 to the 7th. It's 100 times bigger because I multiplied it by 10 to the 2. So we want to talk about the size of things. 1 of these, 10 of these, things get really big really fast. I'll leave that link in the description below for the size of the universe thing, the scale of the universe, and you can see if we go up or down by a power of 10, what that does to the size of things. Okay, check that out. It's very interesting. You probably spend more time doing that than doing this. But we'll see you next time.